4.3, solving polynomial inequalities. All right, who can read this for me? The elevation. Okay, thanks, Lyndon.
Solving polynomial inequality. The evaluation of a hiking trail is modeled by the function x at h equals 2x cubed plus 3x squared minus 17x plus 12, where h is the height measured in meters above the sea level and x is the horizontal position from a range station measured in kilometers. If x is negative, the position is to the west of the station, and if x is positive, the position is to the east. Since the trail extends 4.2 kilometers to the west of the ranger station and 4 kilometers to the east, the model is accurate where x equals x at negative 4.2 of 4.
Okay, so we have a scenario where we're trying to measure the height above sea level from a ranger station, so we can have negative values of x, it's a distance from the ranger station, and we can have positive values in x, that's east of the ranger station, and then our heights are on our y. So we want to know when the trail is above sea levels. So if we have a graph here, something that looks like this, some sort, we want to know what are the intervals between what intervals are these values going to be above 0. Okay? So in order to represent that, we can say, well, we know then we want the height h at x to be above 0. So we let that function that represents the height be greater than 0. Okay, that's what we're trying to find out. Okay? Any questions there? So all we've done is we've taken the equation and we've set it greater than 0 because that's what the question's asked us. They might ask us, when is the height less than 0? In this case, they're asking us when it's greater than 0, so we're saying it's greater than 0. That's where this comes from. Okay, so this inequality is from the question. Are above sea level. Okay, so there's the big tip of the inequality. Okay, so we have a polynomial inequality here. It's an inequality that contains a polynomial expression. Pretty straightforward so far. All right, so the first step that we want to do, if we have a graph, okay, like I drew on the last page, and we have some sort of function happening. There's intervals where it's above 0 and below 0. If we set the inequality not greater than 0, but we actually set it to 0, we can find out these x-intercepts. And if we can find out those x-intercepts, then we can isolate those and know when it's above and when it's below 0. Okay? So we kind of go backwards in a sense where we set this expression back here, not greater than 0, but we set it to 0. Okay? We set it equal to 0. And the reason for that, I'm going to say that again. The reason for that is to identify these points of transition where we go from negative height to positive height. Okay? So we set up the equation with the inequality, so it's important to understand what we're trying to look for. We want to know when they're greater than 0. But then we kind of take a step back and we say, well, let's find out, first of all, what the x-intercepts are. Where are these transitions occurring? Okay, so we set it equal to 0, and then if we set it equal to 0, we can then use our factor theorem and factor it, because that's how we get our zeros, right? When we have a cubic function, the only way we can find our zeros is we use factor theorem. So, what are multiples of 12 over 2? So first we'll consider the multiples of 12 over 1. Okay, so they are 1, 2, 3, 4, 6. Look at that. The first one we try, 1, it works out. Okay, so that's great. We know x minus 1 is a factor. The very first one. Okay, it happens fairly often, right? So now we use synthesis or synthetic division. We divide the trinomial and we get this result. Okay, we can factor this by inspection. And we get this result. Okay, now we have our three x-intercepts. X equals 1, x equals 3 over 2, and x equals -4. Any questions up to here? This is review from last section. Okay, so these are our x-intercepts. So we know then, if here's my graph, at x equals 1, right here, x equals 3 over 2, right here, this is 1, this is 3 over 2, and this is 1, 2, 3, 4, x equals 4, which is over here, -4. We know through these points, what's happening? Are we going straight through? Are we turning around? Or are we having a flattening out?
Straight through.
Yeah, we know straight through because all of these have an exponent of 1, right? Does everybody remember that?
Yeah.
So through all these points, I'm going straight through. I can determine the direction of this one. How? How do I know if it's straight through like this or straight through like this? Yeah. Sorry? Right, so I look at the leading coefficient, I figure out that the degree is odd, so I'm going to have opposite behaviors on my endpoints, and then the coefficient is positive, so I know that I'm going up over here, and I'm coming down over here. Okay, so I know that this is going to look like this, and this is looking like this. Okay? Sorry, this should be more over here. Okay. That's great that you guys know that. However, we do have to still confirm. We have to check points in between here. Okay, so I'm going to show you two ways to do this. The first way is what they've done here. Okay, so they've drawn kind of the same line here. They've just done it on a number line here. And so these are the intervals they need to check. Less than -4, between -4 and 1, between 1 and 1.5, and over 1.5. Yeah, Marco. The vertex of a parabola?
Yeah.
No.
Finding like the maximum and minimum.
No, it's not. No, not at all.
Add up the 2 points and divide them.
No, no, not at all. No, no. It's very different. Okay, so we're looking in between these intervals. Okay, and they show you, of course, the slow way first, and later they're going to show you the fast way. I'm going to show you the fast way right off the bat. So the slow way is they're going to plug in a value in for x that's less than -4 and solve. Okay, so they go back to the original equation, they take -5, they plug it in each time there's a value of x, here, here, and here. Okay, and then they solve and they say it's -78. So is it above 0? No, it's negative. Then they plug it in here, they find out it's 12. So they know it's negative here, they know it's positive here, crosses through, this is 12. That's their y-intercept. Goes through here. They check between 1 and 3 over 2, and they find out that it's negative, so this goes here. And then they check after 3.5, and it's 2, and it's positive. This is a lot of work, though, to check each one of these. Okay, you're checking 4 numbers into the original equation. Okay, so rather than do that, here's another way you can do it. This is how you set it up. So you put the factors on the left-hand side, so x minus 1. Sorry. Let's see. Okay. Here's how you do it. So here are the factors. We're going back to after we use factor theorem. So x minus 1, 2x minus 3, and x plus 4. Okay, factors on the left-hand side. Now the ranges on the top. So we want to do x is less than -4, -4, between 1, 1, Any questions how I set this up? So my range is on top, my factors on the left. Now we can do all the work in our head. Okay, so I'm going to take a value less than -4. You can pick any value less than -4. I'm going to choose -5. -5 minus 1 is negative. Right? Doesn't matter what the value is, I just need to know that it's negative. Next, I'm going to plug in a value less than negative 4 over here. So let's plug in negative 10. So negative 20 minus 3 is negative 23 is negative. Next, I'm going to plug in a value here. I'm going to plug in negative 5. Negative 5 plus 4 is negative 1, negative. So negative times the negative, because they're the factors, which are up here, right? This times this is going to be negative. So this range, we have a negative value. Next one, between 1 and negative 4, I'll plug in 0. So this is negative. And actually, it's easier to go across this way. It just happens to be easier like this. So between 1 and 1.5, I'll plug in 1.1. 1.1 minus 1 is positive. And then over 3.5 is also going to be positive. And there's kind of a pattern that happens. Once you reach positive, the number's going to increase, so it's going to obviously continue to be positive. So it actually works pretty quick. You'll see this as you guys get more practice. This is negative, plug in 0, so it's negative 3. Plug in here 1.1, so we have 2.2 minus 3 is negative. And then we can plug in any number, so 10, this is going to be positive. Okay, positive, and then these will be positive. Okay, so there's this pattern that happens once you switch over, they're positive. And then it's really quick, so negative and negative. Negative times a negative is a positive times a positive. This is positive, this is negative, and this is positive. Okay, so then these are the intervals that were above 0. We're above 0 here, and we're above 0 here. Okay, so the answer to the equation, to the question, when is height above 0? When x is greater than negative 4 but less than 1, and x is greater than 3 over 2. Any questions? So you put the factors on the left, you put the intervals at the top, and you could have wrote these intervals in set notation as well, right? We could have wrote negative infinity, negative 4, and some people prefer this. I actually prefer this. It's kind of a little bit quicker. Okay, there's the set notation. You can write it either way. You can understand set notation better, it'll save you a bit of time. Any questions? No questions? Okay. So here you see that they end up with the same answer. H at x is greater than 0 when x is between negative 4 and 1 and greater than 3 over 2. The difference is the way I did it, you don't need a calculator. You can do everything in your head. It's much quicker. And this might have seemed a little easier at the time, but you're much more likely to make a mistake if you're subbing in negative 0.6 back into here than you are using this method. Okay? And even the book goes to this method on the next example, you'll see. Next one is a graphing strategy. We'll skip that. Example 2. Okay, solve the inequality. So we're given two polynomial expressions on either side of an inequality. The first step is to move everything over to one side. So we're left with 0 on the other. Okay, so we've done that here. Okay, there's no changing of the signs there because it's all addition and subtraction. The next thing we notice actually was we can group factor this, so we don't have to do factor theorem. Always important to look out for that. It's going to save you a tremendous amount of time on the test if that's a question that enables you to group factor. What's common between these two terms? X squared. You're left with x minus 4. What's common between these two terms? Negative 9. You're left with x minus 4. All of a sudden we have all three factors. So we leave the inequality in initially, and then we set it equal to 0, so we change it back to 0 to find the intercepts. Any questions there? Okay, so now you'll see they do it the same method I did in the last example. They put the factors on the left, x minus 4, x minus 3, x plus 3, and they put the ranges on the top. Okay, if you wanted to write it in interval and then they go ahead and they just substitute values. You can do this in your head. Once you get to positive, you can, as the number's increasing, you can assume that it's going to continue to be positive here, right? You can always do that equation. Assuming there's no other intercept. It's not going to go negative. Okay, so they figure out the product here, and now they know the two ranges when the value is greater than and equal to 0. Any questions there? It's the exact same process. Number 3, selecting a strategy to solve a polynomial inequality that is unfactorable. So this we can't do without graphing. We need a graphing calculator here. We're not going to do it, but if I want to make it aware how you would solve this, okay? Because I might give you the graph, and you still need to know how to solve it, okay? Yeah.
Will you ever give us a question that's unfactorable and how to test? No.
Yeah. There's been questions already that have been unfactorable, just like in grade 11. Okay, so we have this really long expression, and then we want to know when the height is above 9 meters above the ground. Okay? So, the only thing I want to make you aware of, what you would need to do for this, is you would have to look at the graph and draw your 9 meter line, and then these would be the intervals that it's above. Okay? So you would read these intervals off here. Okay, and that's because it's above 9 meters. Any questions there? You're given a graph, you're given 9 meters above the ground, you draw the line and you read off the intervals. So it would be between 5 and 20 and 40 and 49-ish. All right, in summary, to solve a polynomial inequality algebraically, you must first determine the roots of the corresponding polynomial equations. So these are the x-intercepts, right? Then you must consider the sign of the polynomial in each of the intervals created by the roots. The solution set is determined by the interval that satisfies the given inequality. So given inequality, this is from the question. You need to know some polynomials inequalities can be solved algebraically. Inverse operations, factoring, using a number line to determine and a table to determine the intervals on which the polynomial is positive and negative. That's what we did. All polynomials inequalities can be solved using graphing technology by graphing, determining the intersection points, examining the graph, creating an equivalent inequality with 0 on one side, identifying the intervals created by the zeros of the graph of the new function, and finding where the graph lies above the x-axis or below, as required. So that's pretty self-explanatory. Any questions with this lesson?